So let me review what we said in the two lectures. We started by defining the symmetry. We coupled the system to background gauge field. We limited ourselves to flat gauge fields. And then it's enough, we can specify the background gauge field by having patches and transition functions and so forth. But then, since it's flat, all the information is in the transition functions. And then we interpreted them physically as defects and operators in space-time. And these are unlike the defects that Zohar talked about, because the defects that Zohar talked about are not topological. In fact, he computed various quantities as a function of the size and so forth of the defect, whereas the defects I'll be talking about are topological, which means that we can move them around, we can bend them, and so forth. And that's a statement that they reflect underlying symmetries. So the fact that there's an underlying global symmetry means, it's topological to the statement, that the defects are topological and we can move them around. However, sometimes the defects are not completely topological. They are invariant under small changes, but they're not invariant under larger changes. And that came about in the sense that the partition function might depend on various phases, and we presented examples of that in the continuum in various examples. The simplest one was the two-level system with vanishing Hamiltonian. That's an example of a system with an anomaly. So when this thing happens, we say that there's an anomaly. And then we talked a little bit about the C=1 system. I said it has an anomaly, but I haven't exhibited it yet. I'll exhibit it today. And then we also saw a peculiar feature of the C=1 system, that if we simply put the system in a chemical potential, and even if we break the winding symmetry, we get it back for free, which looked very mysterious. It's unlike what we learned before. And then I gave a better, more conceptual explanation of why it happened, because there's some kind of an anomaly involving translation in the presence of a chemical potential. Now, this whole thing might make you feel a little bit uneasy, that maybe I manipulated, this whole thing is very subtle, and maybe I manipulated the field theory somewhat carelessly. Maybe there are some divergences, and there was a whole discussion of whether this thing has anything to do with divergences, and I forcefully said that this has nothing to do with divergences. And with that in mind, I would like to present the whole thing on the lattice. So we have a finite lattice, finite number of degrees of freedom, manifestly no divergence. So we have a quantum mechanical system with a finite number of degrees of freedom. And what I will do today, I will show that such a system can have anomalies, can have defects. The defects are subtle because of the anomaly. And we'll explore some of their features. And in a way, this would be overkill, because this would be an exactly solvable system. And you could say if the system is exactly solvable, why am I bothering with all these subtle things? And the point is that in the next lecture, I'll present another system which might or might not be exactly solvable, including some systems that are not exactly solvable. And then these considerations will be very powerful and will connect to many results in field theory and in condensed matter physics. So before I review the last part of last talk, the last part of the recent talk, are there any questions about what I said? Okay, so let me state it very carefully. Defect, the terminology I use, defect is something that stretches it along the time direction. Operator is something that acts at fixed time, isn't it? If we think of it as a Euclidean field theory, there isn't a distinction. So we just get that. And these particular defects that I'm talking about, either defects or operators or something which goes diagonally in space-time, are characterized by the fact that as any operator crosses them, it undergoes a transformation by the global symmetry. Does this answer your question? Yeah. And I'll try to be careful with the distinction between defects in operators, partly because from this point till the end of these lectures, I have this one and another one, I will have a non-relativistic system on the lattice, so time will be continuous, space will be a bunch of points, finite set of points, possibly large, but finite, and we don't have Lorentz invariant. So any quantity, any consequence of Lorentz invariant should not be mentioned. So I'll try to do as much as possible without assuming Lorentz invariant. And I should just say that this is what happens in many realistic systems. Like if you have the lattice actually exists in the lab, and it's not Lorentz invariant, and so forth. So we talked about the
question. So the question is, why is it important to identify all the anomalies? I mean, will they be a tool to solve the system that otherwise you cannot do it? It's like the matching of two anomalies?
Yeah, not like. It is the matching of two. It's exactly the same as the matching of two, except that the symmetries will be a lot more subtle, and I will be on the lattice, so that I don't have Lorentz invariance. So the idea is that Tooth told us that if there's a global symmetry, we have a Tooth anomaly matching. As before, it doesn't solve the system, but it gives you a constraint on what the possible solutions are. And I'm going to do exactly the same thing, except that instead of being in the continuum and instead of being Lorentz invariant, I'll be on the lattice. We don't have Lorentz invariant. We don't even have continuous translation. So that would be one distinction. And the second distinction is that we'll have all sorts of subtle symmetries that can have anomalies. And these subtle symmetries, as we will see, are not symmetries that we usually discuss in the continuum, but they lead to interesting consequences. And the outcome of that will be constraints on the long distance behavior, constraints that some of them had been known before, not in this language, and others are new. So just before you complain, I'm not going to, if the system is solvable, I'll solve it. But if it's not solvable, this does not help you solve the system. It only gives you a constraint on putative solutions. Exactly as in a tooth. It's not going to be better than a tooth, except that it applies in a slightly different context. So we were interested in the C equals 1 system. And I remind you that in the continuum there's a parameter R, and at R equals 2, there's a BKT transition. The system here is gapless, and here it is gapped. And it's gapped because winding operators become relevant. So what we're going to do is ask ourselves, how can we tune the winding operators so that they will not be here? In other words, in the continuum, the model is gapless for every R, and there is exact T-duality that maps out to 1 over R and so forth. But if we work on the lattice in these models, we have a transition, and there are vortices, and the vortices proliferate, and the system is gapped. And I would like to have a system which has exact momentum and winding symmetry on the lattice. And then we can try and break the winding symmetry to see the consequences. One reason I'd like to do that is that we know that in the continuum, we have an anomaly. There's no anomaly within the momentum symmetry, but there's a mixed anomaly between winding and momentum, which I did not discuss. And you could ask, can we see this anomaly on the lattice? That's the goal. We'd like to see this anomaly and its consequences on the lattice. And the reason I did not discuss it in the continuum is that today I will do it directly on the lattice, and then it will trivially follow how it works in the continuum. So this is the introduction. And we started yesterday with the rotor model, which had the circle-valued field at every site, and the conjugate momentum at every site has integer eigenvalues, and there's a cosine interaction between the sites. And we wanted to write it in a Villain form. So we ended up yesterday with the following Hamiltonian. We have a sum over the sites, J. We have some coefficients Ju over 2, Bj square, plus J over 2, phi J plus 1, minus phi J, minus 2 pi n J plus 1, quantity square, minus G square, sum over j, cosine, it's always the problem. Square, I can put it 2, doesn't matter, or sum over j, even to the power I j plus 1 plus complex conjugate, and this is it. And now I have used different normalizations yesterday. So this is the Hamiltonian. Yes?
I understand momentum, but how do you think of winding in this model?
I'll get to that. That's the hero of today's story. So as you said correctly, we have a momentum symmetry, Qm. This is the charge, and it is sum over j of pj. Right? This is the generator of the momentum. And I'm going to call every one of them sum over j, q momentum at the side j. Right? So qj momentum is pj. So what this equation tells us, that this is a charge, this is the charge density, or the zeroth component of the current, and it's given locally by the momentum. And it implements translations in the target space. This model does not have the winding symmetry, as you correctly said, does not have the winding symmetry. And in fact, there's some parameter, u and j and g, there's some function of them translates into r. If j is sufficiently big, this operator is irrelevant. We are in this phase. There's a formula, r is a function of these coefficients. And as we vary the coefficients, r changes. And at the point that corresponds to r equals 2, there's a phase transition to a gapped phase, because this model doesn't have the winding symmetry. This model is essentially the same as what is known as the Villain model, which was discussed mostly in the Euclidean version of this. This is Lorentzian description, was done mostly in the Euclidean Lagrangian interpretation. That's the Villain model. And it also has these two phases. Okay. The advantage of this model, yeah?
You started without the gate field, right? And then you added in.
Yeah.
So it's a different model?
Yes, absolutely different. Very important. So the model without the gauge fields, so we dropped this and we dropped that. That's a model of phonons. Phi is a non-compact field. We can go to normal modes. It has exact R internal symmetry, not U1. Phi is non-compact. We can shift phi by an arbitrary real number. And as we shift phi by an arbitrary real number, it's a symmetry of the problem, and it's a different one. Now, in a fancier language, I could say I would like to make phi compact. The way I do that is by gauging the group of integers. So originally the target space was R, and I would like to go to mod Z, which is the same as S1.
And this model is equivalent to the model you wrote in the beginning with the cosine?
That's correct. It's not equivalent, but it's closely related. So this model and the model with the cosine, known as the rotor model, are very similar. And there's a dictionary between the parameters there and here and the parameters there. We can add all sorts of other terms on the lattice. That would change the dictionary of the parameters, but the critical behavior is the same. And neither has the winding symmetry, and both have this big AP transition. But in terms of R, they happen at the same place, because that's the continuum description. But in terms of the lattice parameters, they happen at different places.
So in a sense, you started with the theory, you simplified it by assuming that phi is small and make it a continuum, and then you go back in some sense to the original theory?
Not the original, but the cousin of the original one. So that phi would be circle-valued. So, and we have commutation relations, that phi is conjugated to P, and N is conjugated to E, and I wrote the commutation relations yesterday.
What's the role of velocity?
It's allowed. So E is circle-valued. Since N is quantized, E is circle-valued, so you can't stop me from adding this term. And this term is the analog of the electric field square. So if you
can villainize the square.
You can villainize and add more, but then something else will
Instead of cosine, you can write it the same like
you could, and then there would be another field, and soon this will appear. I'll soon do that. But at the moment, we just take this guy, And if you start from the Villain action in Euclidean space that you know and you worked on, and you just follow your nose and find the Hamiltonian, you will find this term. You find this term. This term essentially starts from, in Euclidean space, from the plaquette interaction of the ends. On the lattice, you can write a plaquette term for the ends, and it converts into this one. And there's a more systematic way of deriving it. So this model, you could say, is a complicated or simple way of thinking of the model we discussed originally in the continuum deformed by winding, or the XY model, or the rotor model that we have here. The main point, which has a complicated history, which I'm not going to review, so I'll just do it here without any references. Okay, you say, let's take this model and set G to 0. So I'm just going to set G to 0. And therefore, if I yesterday had a factor of 2 here or not, doesn't matter, because I'm going to set G to 0. And I guess this is what Shmuel had in mind. He asked, why did you add this term? The point is that once I drop this term, the model actually has the winding symmetry. So this is the very efficient way of creating the winding symmetry on the lattice. See, originally, the logic was that at every site we have a rotor. The winding symmetry tells us as we go along the lattice, it counts how many times the rotor, the phi changes, how many times it winds around. This makes sense when phi at one site and phi at another site are near each other. But if you have phi that is completely random, you cannot define winding. I claim that in this way of writing things, you can define winding. But before we do that, I want to review one more formula from yesterday. So this model, even with G, is a Gauss law. At every site J, we can have I wrote this formula yesterday, e to the I, e j plus 1, did I write it this order? Yeah, minus e j minus 1 j, minus 2 pi I bj. And you can check that this object at every j commutes with the Hamiltonian. This is straightforward computation. And since it commutes with the Hamiltonian, I can restrict the Hilbert space by imposing this Gauss law. So if you're more familiar with gauge fields in the continuum, I claim that this is the analog of E square. If you expand it in small e, it becomes E square. And this is the analog of Gauss law because this is the divergence of E, and that's equal to the charge density. And furthermore, if we take this thing, so imagine you impose this condition. Let's multiply that over the whole lattice. Then the e's cancel in pairs, and we are left with e to the minus 2 pi I, sum over pj, which is e to the minus 2 pi I times the total charge, and hence the total charge is quantized. Okay, so now finally, we can kill this term and check the consequences. The first thing I want to do is connect that to what we had in the continuum. So if we were continuum people, we would say, let's choose a gauge. We had this gauge symmetry that we discussed, that all the ends are 0, at least locally. And then this becomes a derivative. And this is the momentum conjugate weight. So I'm going to write the Hamiltonian is 1 over 2 r square, sum over j, pj square, plus 1/2 r square, r over 2 pi square, phi j plus 1 minus phi j minus 2 pi n j plus 1 quantity square. And I can put here the sum over j. So This is the Hamiltonian, and I express these lattice coefficients, U and J, in terms of R, with the parametrization that can be easily derived in the continuum limit, as the phi's are near each other. And I've already set G to 0. I've already set G to 0. And I think not in this language, but in another language. This was actually done first in a paper by Gross and Klebanov. It's this thing of setting G to 0 is closely related to something that they did a quarter of a century ago also. Maybe even more. It's more than that. 30. 30 years ago? No, it was, yeah, in prehistoric times. But now we have something new, because consider sum over the lattice and J. I want to get the coefficient straight because it's very important. Minus, I won't put a minus here for reasons that will be clear, J plus 1. We can think of this as the Wilson line of the Z gauge field. It is gauge invariant because we say that the gauge symmetry shifts n by an integer on one side minus the integer on the other side. So when we consider the sum, it's gauge invariant. We have periodic boundary conditions.
That's a Wilson line.
Sorry?
That's a Wilson line.
That's a Wilson line of the Z gauge theory. So we can think of this as being these n's and these e's as being Z gauge theory on the lattice. So this is a Wilson line, so we can call it W. At this stage, W stands for Wilson. And this is also winding, yeah, it's very efficient. This is the winding number. And it's a symmetry only because we excluded this term. Because this term doesn't commute with this. The e's don't commute with the n's. And I excluded the term in the Hamiltonian, and therefore it commutes with this symmetry charge. So this is a symmetry charge. It's integrated along or summed over space, and it commutes with the Hamiltonian. So we can also call it QW. But there's an important difference between this charge, the way it's written in terms of the charge density, and this charge, the way it's written in terms of the charge density. So this is an integer, and this is an integer. But the difference between them is that the charge density here, or this is the charge density, J sub 0, the time component of the current. That's a good operator. But here the charge density is not a good operator. Can anybody tell me why it's not a good operator? It's not gauge invariant, but it's easy to fix. Now it is gauge invariant. So I haven't done anything because these guys cancel in pairs in the sum. And I'm going to call this one as sum over J, using the same notation as there, QW at the point J, J plus 1. So the momentum charge density lives on the sides, and the winding charge density lives on the leaks.
Is it squared?
No square, sorry about that. Oh, I'm so happy when people correct me. I'm happy not because I made a mistake. I make mistakes all the time. That doesn't make me happy. But the fact that people follow and understand.
It's on the lattice, now we can actually follow.
Sorry?
It's on the lattice, now it's like we can actually follow.
I thought it would be exactly the opposite. So this model on the lattice has the following symmetry. We have U1 of momentum, we discussed before. We have U1 winding, which we discussed here. And we also have a Z2 that flips the sign of everything, flips the sign of phi and N and P. This is exactly the symmetry of the continuum model. Okay, so we have two interesting objects. Let's recall what they are. The charge density here is Qm of J, which is Pj. And the charge density here is QWJ, j plus 1 on the links, which is 1 over 2 pi, whoops, no sum, phi j plus 1 minus phi j minus 2 pi m j plus 1. Whoops. And when we have two charge densities, we can compute their commutator. It's completely, this model, I should say, is completely solvable. The Hamiltonian is quadratic. Still need to impose this Gauss law. It's completely solvable. But I'll pretend I don't know that it's solvable and just get consequences. So let's compute QMJ with QW2 J prime plus 1. And I'll use the same notation as here. Okay, here I wrote it in the opposite order. So let's compute the commutator. So first of all, every commutator has an I. That's because we have momentum and coordinate. This thing actually commutes with this, so we don't have to worry about it. The whole thing comes from here. So we have phi and p, so that gives us an I. There's a 2 pi that we just copy. And then we get delta functions. It's a straightforward computation. Who under the age of 16 knows the name of this term? So you just became much younger, Shimon. What?
I want to feel
So this is known as the Schwinger term. And it's very interesting because what it's, well, I think Schwinger did it in the continuum. And if we sum either over this or over that, I think I left out the prime. If we sum over j prime or we sum over j, this thing vanishes. So the commutation relation of a charge with a charge density is 0. That's good. So charge with charge is 0. Even charge with charge density is 0. But the densities don't commute. So Schwinger did it in the continuum. And here it's down on the lattice. And this is the first signal that there is an anomaly. In fact, some people say it's an anomalous commutation relation. And now we see it on the lattice. And in fact, we'll soon write it in more detail, but imagine that the number of sites on the lattice is 1. There's only one site. It's a very degenerate case. There's no difference between the charge density and the charge, because there's only one charge. And this thing indeed vanishes, and we have the symmetry. Next case in complexity, the number of sites is 2. For 2 sites, the charge and the charge density are not the same. The charges commute. The charge commutes with the current, but we can see the anomaly already in the lattice with 2 sites, because this thing is non-zero. So when I had to defend the point of view that anomalies, even in field theory, have nothing to do with divergences, I present that, and I rest my case. I hope this convinces everybody. Let's see where it came from.
So, Nati, but is it not a different definition of anomaly? Now we
No.
consider why is the commutator of charge density?
I'm going to show you that this thing is what we normally call an anomaly. In fact, the definition that you like uses that as the definition of anomaly.
start with this and get that.
Yeah, you get everything. Yes, I'm going to get all the consequences.
Yesterday you had a comment about the Gauss law being an integer or phase. You had something about that.
Yeah, so I have to impose this to be 1. Everything I do is in the subspace where I satisfy this equation, and this has to be 1. So the thing in the exponent has to be quantized, not necessarily every term separately. Not necessarily every term. But when I looked at the total charge, so I multiply these guys over the whole lattice, then this does quantize the charge.
Nati, the surprising thing here is that we expect things to commute because of the direct product. No?
That's right. So because of the direct product, as a group, they commute. They commute as a group. but the currents do not commute. That's the anomaly. The anomaly is that the currents do not commute, even though the charges do commute. But they fail to commute in an interesting way. Well, it has to be local, because things sorry? It's a derivative of a delta function. This is the discretization of a derivative of a delta function. And I emphasize that we can see it for a lattice with two sites. So we approximated the derivative of a delta function on a lattice with two sites. Let me make one more point. My first attempt at describing the winding charge was to write this expression. That's the Wilson line. It was not gauge invariant. But you could say, who cares? We work in a big Hilbert space. This is an operator in a big Hilbert space. It doesn't commute with Gauss' law. So let's follow that. If we do that, then we don't have the phi's here. So we don't have the phi's here. And then we get 0 on the right-hand side. This is characteristic of anomalies. You would like it to, you can avoid this anomaly at the expense of not preserving the gauge symmetry, the Z gauge symmetry. I preferred to impose the gauge symmetry, impose Gauss' law at every site, and therefore I had no choice but to introduce these phi's here. And once I introduce the phi's here, they fail to commute with P that is here and gives me the Schindler term. Just to show you how this thing works and how it's connected to what we discussed earlier, let's be very degenerate and look at the model with L equals 1. This is a field theory with L equals 1, although it's perverse to say that this is a field theory, but if you don't understand quantum mechanics, don't start with field theory. So what's the Hamiltonian? I just copy. So the Hamiltonian is 1 over 2r squared, p squared. I don't bother to write the j, and I have plus a half r over 2 pi square. That's my r, and I don't need to write the sum. There's only one side, so these two guys cancel, and I get here 2 pi n. There's only one n because there's only one link square, and you immediately recognize the formula for momentum square plus winding square that we had in the first lecture. So that shows that we are on firm footing. And I will leave it as an exercise for you to work out the system with two sites. So, and this satisfies Gauss' law. Gauss' law is automatically satisfied here. And what it does is to quantize the p's. The p's are integers. That follows from Gauss' law. So that gives all the right answers. And I'll give it as an exercise to work out L equals 2. So now there are currents. And I'll tell you what the answer would be. There would be a P, there would be an N, and there will be one harmonic oscillator. And that's all there is. There's one harmonic oscillator, one P, quantized P, and one quantized N. And they have a spectrum, which is the spectrum that we want for quantizing the C equals 1 system, but with one harmonic oscillator, not an infinite number of them. So that's not surprising. Questions? None. Another nice feature of this model, who asked me before whether I can villainize it? Shimon. So finally I get to this point. Oh, I think I did erase what I needed. Oh no, I have it there. I'm going to change variables. So wherever I saw Pj, I'm going to write 1 over 2 pi, phi tilde j plus 1, minus phi tilde j minus 1j, minus 2 pi, and tilde j. And wherever I saw would be a conjugate momentum, j plus 1, which is 1 over 2 pi, phi j plus 1, minus phi j, minus 2 pi, and j plus 1. Just 1 second. E to the I e j plus 1. I'm going to write it as e to the I and e to the I, e tilde j equal e to the I phi j. Yes, Peter.
If we have periodic boundary conditions, then we also have the cyclic symmetry.
Yeah, these will be very, very important soon. You'll hear more about the cyclic symmetry than you ever wanted to hear.
It's never enough.
Not enough. Good. So we are the rule that whenever I teach students and postdocs, go after the symmetry. Go after the symmetry. When confused, try to identify the symmetries and try to go from there, because that's the way not to be confused. And I guess that's what you had in mind. There's another symmetry here. I haven't yet used it. I should use it, and I will. Notice what I did here. Originally, we had this was simple, and that was complicated on the sides. So I'm going to redefine variables such as this will be the new p. This is p tilde. And instead of e, I have the new field, which now lives on the links. And that's in the spirit of who wanted me to you wanted me to villainize it? That's what I'm doing here. And if I do that, I leave it as an x, well, I'll write the answer. The original Hamiltonian, I'm just doing this change of variables, becomes sum, a half, 1 over 2 pi square, phi tilde. Now the phi's are on the links. J minus 2 pi n tilde square plus 1/2 L square p tilde j square. So the Hamiltonian went back to itself, except that the matter fields now live on the links, the gauge fields now live on the sides, and R was interchanged with 1 over R. What happened to Gauss law? The original Gauss law, if you substitute this thing here, is satisfied automatically. So we don't need to impose Gauss law. So in the new variables, we don't have to worry about Gauss law. Gauss law is satisfied automatically. However, we need to impose another Gauss law instead. And there is a G tilde, which is on the links, j plus 1, which is e to the I, e j plus 1 minus e. That has tildes, everything has tildes. J minus 2 pi I pi tilde j plus 1 equals 1. This is common when we have what is known as dualities. In dualities, what's obvious in one frame is not obvious in the other, and vice versa. Gauss law is automatic in one set of variables, but not another. So usually the equation of motion and Gauss law changes role. And we see the same thing here. This is, by the way, a duality transformation. The links and the sides change role. The gauge fields and the matter fields change role. And Gauss law, the original Gauss law, is now automatic. But instead, we need to impose a new Gauss law, very much like in ordinary duality. Except that we do it on the lattice, and that's common. But we are in a system with anomalies. So the reason this is interesting is that we want to study the anomalies and see how to think about the anomalies. This is known as T-duality, for reasons that are far from obvious in the line of reasoning that I present here. Questions so far?
Just one question. You are in some variable you are using j and j plus 1, and in some variable you are using just j. Is it very necessary, or it's like
It's the natural, yeah, it's not necessary. You could say everything is on the sides,
Yeah.
but this is a much more convenient one, because when you talk to two different sites, this is an,
okay,
the link.
whether it's a link or a site.
Yeah. So since we are in one dimensions, it doesn't really matter.
Yeah.
Even in high dimensions, you work to write more if you can. But this is geometrically, this is the better way of thinking. Okay.
One feature of T-duality, which is not visible for a single scalar, but would be visible for many, would be mixing metric and target space and B field.
Yeah, I believe this. I believe. Yeah, I believe this would work here. I did believe this would work here. I haven't checked it. I believe it works. I believe it works. I haven't checked it. Having said that, another thing when you started asking says one feature of T-duality is that you could ask what happens at the self-dual point. In the continuum, we get an enhanced SU2. Here we don't. The exact SU2 does not follow, and it exists only in the limit. The exact SU2 exists only in the limit.
On the lattice, nothing.
And the lattice, there's nothing special, but it doesn't have to. But I asked you to, I suggested that you work out the theory at L equals 2 and check whether indeed the spectrum does what I said, and you'll see that there's no SU2. In fact, I did do the case of L equals 1, and already there you see that the spectrum is not in SU2 representations. So the SU2 exists in the continuum, but it does not exist on the lattice.
So if you already look at these issues, there is also the point where the Orbi circle meets a circle. Do you see that feature?
Yep. Yeah. It's a property of the spectrum of exponentials. The spectrum of exponential is just exactly as in the continuum. I showed it on L equals 1, and it's the same way in others, and what you just said is a property of the exponentials. It's the oscillators. See, in the continuum, we have an infinite number of oscillators. The oscillators, we truncate the number of oscillators, and therefore we don't have the full features of it. But whatever is independent of the oscillators exists already.
So the zero modes?
The zero mode, yeah. Yeah.
Could you explain how Gauss law is implemented maybe?
The one that we lost or the one that we need to impose?
The one that we lost.
The one that we lost, you just take these P's and E's and substitute them in, so the 5 tildes will cancel, and you'll get with an n here, but n is an integer, so it's automatically satisfied. Right? What's Gauss law? Gauss law takes difference in E's and P's. So the difference in E's will give me 2 5 tildes in the exponent, which will exactly cancel these 2 5 tildes, and we'll be left with n, but n is an integer, so it's automatically satisfied. However, this change of variables reproduces the old answers only if we impose this equation.
But the enhancement to SU2 does not involve oscillators.
It does, because otherwise you don't have SU2 multiplets. You need to have the currents in the right place. The spectrum is not. The spectrum, as I described, is not in an SU2 representation. I can do that in more detail. You don't even have enough states. So imagine L equals 1. So you have only the pure exponentials. The pure exponentials, you don't have the oscillators at all.
The currents themselves, you have exponential those that enhance the U1.
The states in the spectrum are the states I mentioned. There's no current. If L equals 1, there's no current. There's only the charge.
Okay.
There's another question?
Do you have some intuition for the emergence of the SU when you continue?
No. No. Yeah, this actually I've lost a lot of sleep over this question. And I would love to have something. Because there's a new symmetry that we get in the continuum, and I don't see any precursor of it on the lattice. But I do see all of these symmetries.
Well, you see self-duality.
Sorry?
You see self-duality.
I see almost self-duality vaguely. If I look more closely, the duality exchanges things from the sides and the links.
This can be described exactly by SU2 symmetry.
That's true, but it's the self-duality to the extent that it exists that you see here is Z2. We don't see the full
That's the
SU2.
Z2.
The Z2 I can sort of see because it exchanges links and
That's
sides.
the heap.
Yeah. There are situations where there's self-duality in the discrete group, which is not embedded in a continuous symmetry.
I'm not sure. Anyway, I have to recall.
Yeah? The Ising model at the self-dual point. Maxwell theory in 4 dimensions.
No, I was talking about free-field theories in 2 dimensions.
Okay, so, yeah, you're right. And this theory is free, and it might be misleading, and we might extract misleading general comments, or we might want to have misleading general results. But I would like to keep the discussion general because I'm going to apply the same line of reasoning in more complicated systems where it's not so obvious.
So Matti, the Orbi circle line, can you device?
I believe, I have not analyzed it in detail. I'm almost certain that you can gauge another Z2 here and derive the other line.
Against bound?
That I doubt you can do, because you need the full SU2 for that. But what you need here is to gauge this Z2. That's what you talk about. You talk about gauging this Z2. And since the Z2 is there, since the Z2 exists here, I think I should be able to gauge it. I haven't analyzed it in detail. Yeah. So why are we doing all this? We're doing all this because we want to study anomalies. We want to study anomalies using defects. So this system is good because I can analyze the defects and see how to probe anomalies. We'll learn properties of the defects.
One last question.
No. I really ask you that this will not be the last one.
Can one impose a crazy constraint that 5j is equal to 5 hat jj plus 1?
No, they don't even leave at the same point.
You don't leave at the same point, but
Yeah, maybe you,
canonically,
I believe this might be in trouble. You might be in trouble with the commutation relations. I believe. I haven't thought of it, but
continue with we don't have trouble. In continue it would be just selecting the chiral part.
that's right. But even that is not true. The chiral file by itself does not make sense. You need to make more choices.
That's my choice. I say that I identify the link variable with the left hand.
Okay. Let me rephrase your question in a way that you'll be more satisfied. Let's take this model as a function of r and specialize to the point r equals √2. At that point, this is one Dirac fermion. At that point, we can try and construct out of this model just the left-moving parts.
That's what I'm
That's what you make. Because in the SU2, you cannot quite do that. Okay, that's another theory, but it depends on more choices. And it's not modular invariant, and it's not modular invariant, and so forth.
It's not modular invariant also for finite number of links. It will not also.
But it is modular invariant in the sense that I will soon make precise. This thing has a T, not S, but T in the way we would like it to have. And the other model does not have T the way we would like it to have.
Because it's frozen.
No, because you have states in the Hilbert space with fractional momentum. But the states here have whole integer momentum. Momentum I mean space momentum, not target space momentum. So in that sense, it's not. But this is really putting the cart in front of the horses. So what do we mean by a defect? So we can study two kinds of defects, momentum defects and winding defects. The winding defects, although he didn't describe it that way, have already been discussed by Zohar this morning. It's not obvious from what I said so far. So Zohar told you this morning to study Wilson lines as defects. So imagine we take a Wilson line at fixed position in space running along the time direction. This is like background charge of the gate symmetry. So we're going to do the same thing here. So the Wilson line is the sum over the ends. Putting it in the time direction is like putting background charge for that Z gauge theory. This is the same as taking the same Hamiltonian picture, and let me erase this that I don't need, and modifying Gauss' law at one point. So we introduce a defect by modifying Gauss' law at one point. So Gauss' law told us that this is 1. So I'm going to put here a phase, e to the I, and I call it eta sub w. And it could be any fraction, any phase. So I modify Gauss' law only at one site.
It should be
Delta J, big J. Who asked about delta? Good point. Sorry? Are you giving him credit?
No.
Okay, so I modify Gauss' law at one point, and I claim this is a defect. I didn't touch the system at different points. So the system, without imposing Gauss' law, can be thought of as a system with all possible defects of all possible charges at all possible places. But I'm going to choose just one of them. So it's a different Hilbert space, because out of the big Hilbert space, I select a different subspace. You might feel uncomfortable that I changed the Hilbert space. You'd like to keep the Hilbert space as is. Fortunately, it's very easy. I just redefine P at that point to absorb this eta in P. So I now have Gauss law retains its form. Everything is the same, but I modify the Hamiltonian. So the Hamiltonian, 1 over 2 R square, sum over j, not equal to big J, bj square, plus 1 over 2 R square, pj. Now let's see the signs and the 2 pi's. Plus eta w over 2 pi square plus 1 over 2 r over 2 pi square sum over j. And I'll write it like that. I'm not going to bother to write all the indices. Square. I hope this shorthand notation is clear. So all I did was to take one side, and at one side I changed the momentum. Has anybody seen, imagine you had only one side. What is this term called? It has a name. Sorry? Good, close enough. Is there another name? Such a term in quantum mechanics has a name. It's also in field theory. It's called the theta parameter. We shift the Hamiltonian by a fraction. So what we do is keep the Hamiltonian as it was, keep the Hilbert space as it was, except that on one side we introduce a theta parameter. So the theta parameter in that term tells us that this combination of p's can now be a fraction, and that would be a winding defect. Now, is this a good winding defect? Problem number 1, the symmetry was U1, not R. The winding symmetry was U1. So is eta W the same as eta W plus 2 pi? I'm asking. We did a twist by a U1 transformation, so that too should be the same. In fact, in the presentation, using modification of Gauss law, it's obvious. How does it work here? It works here because the Hamiltonian, and I'm going to suppress all the indices that are not important, eta W is related to the Hamiltonian eta W plus 2 pi by a unitary transformation, I, pi j, and this is e to the minus I, pi j. That's very important. On general grounds, eta and eta plus 2 pi should be the same point. If we look at the Hamiltonian, they are not. But the Hamiltonian is conjugate to the one with a shift of eta. The reason I go very carefully through that is that in the first lecture I said that when we specify all these transition functions, the transition function should take values in the group. Here, we're in danger that this is not in the group, because it's not manifestly invariant under shifting by 2 pi. But they are invariant up to conjugation. So when we'll go for anomalies very soon, we will see that these conjugations will play a crucial role. It's very important that when eta is the same as should be the same as eta plus 2 pi, this is not quite true, but it's true up to conjugation, which is the first sign that something could go wrong down the road. The second thing is that I said that the defect should be topological. So the question is the Hamiltonian with the defect at the point J with eta W, is it the same as the Hamiltonian when I put the defect at the point J plus 1, eta W? They are not the same. It's not the same Hamiltonian if I shift. Not the same. However, they are related by a conjugation. There is a unitary transformation, which I'll call UW J plus 1. The unitary operator W, where UW J plus 1, this is U, equals e to the I, eta W, QW J plus 1. So first of all, you can check that this thing does the job. If you conjugate the Hamiltonian, it moves the defect. What's the physical interpretation of this formula? So we have a defect at the point J, labeled by a twist eta W, the point J. And at some point, we would like to continue time evolution with the defect at the point J plus 1, with the same eta W. What do we need to do? We need to move it from place to place. The way to do that is to introduce here something. And since this is vertical, it's a defect. Since this is horizontal, it's an operator. And the operator that moves the defect is the same. In the continuum, this thing becomes this. It's smooth. So this is a line segment where I integrate the corresponding current. So I had a charge which is integrating the current over all of space. Here I integrate the current only over a segment. And therefore I'm not surprised that what I see here is the charge density. So the operator that conjugates the Hamiltonian to move the defect is the charge density, exactly as we would expect in the continuum. Next, let's compute the total charge. The total charge, we define total momentum charge. So we have a system with a defect. It would be Qm, J, sum over J. What do we mean by Qm? If we say that Qm is the sum of the momenta, the momentum here is a fraction. So this is the same as Qm m for eta equals 0 plus eta w over 2 pi. So this is with eta. What do we see? That this defect carries fractional momentum charge. This defect carries fractional momentum charge. And you could say that this is a C number, and maybe you want to redefine it away and not consider it. This is an option to keep in mind, and we will soon see whether it's a good thing to do or not. But if we just follow our nose and say what we write here is determine the Hamiltonian, we end up with the defect carrying fractional electric charge. This result, by the way, is known in the continuum. This is the statement that when we do spectral flow, we do spectral flow by eta W, then the charge gets fractional contribution.
It was called the Witten effect.
Yeah, the diode, the charge of the diode.
Okay, in the context of dions, this is indeed the Witten effect. This particular thing was known long before Witten. In the context of Kac-Moody algebra, this is known as spectral flow, and that was done long before Witten. It's also done in exactly this system. So the fact that it was later used in a different system, if we can easily repeat this story in 3+1 dimensions, it's straightforward, and then what you said would be correct. Again, we can have Wilson and Truth lines, and then the Truth line will carry an electric charge, and then it would be completely correct to call it the Witten effect. What did that do? Okay, this is winding charges. And after this long discussion, it should be straightforward to introduce momentum defects. And we already know that they are essentially the same, but it's worth writing it down because, as always, when things are essentially the same but not quite, the place where it's not quite teaches you something. So we can do the same thing. We did it with in the dual variables, it would be identical, but we would like to stay with the same set of fields. But it's clear what we did. Here, we shifted one term, we picked one term, and we shifted the momentum. Here we're not going to do that now, so now we're going to put momentum defect, the point j plus 1. It would be on the link. So we have 1 over 2 r squared sum over j, bj squared, plus 1 over 2 r, whoops, no. Now we have the complicated one. So it's 1/2 r over 2 pi square, sum over j not equal to j, delta phi minus 2 pi, and I will not bother to write the indices. And now we have to add the new one, r over 2 pi. And we have delta phi. Let me write the full thing. Phi j plus 1 minus phi j. J plus 1 minus phi j minus 2 pi n j plus 1. That's what we had before. And all we need to do is add here plus eta m 180 squared. So we take one link and we change the Hamiltonian on one link and nowhere else. And that's the momentum defect. Such things are common. And there's a similar thing in the icing model, was first done by Kadanoff and et al. We take the Hamiltonian or the Lagrangian, we pick one link. So in the Lagrangian, we have to do it at all times. So we pick a line through Euclidean space-time. Here it's the Hamiltonian, we pick one link. We change the Hamiltonian at that link. Before, we change the Hamiltonian at one site. This is clearly localized. The Hilbert space is the same. The local dynamics away from the defect is the same, and we just change it locally. And we can go through the same set of questions. First, is eta m the same as eta m plus 2 pi? Naively, the answer is no. The Hamiltonian depends on eta m and not only eta m plus 2 pi. However, can anybody complete the sentence? Thank you, David. The answer is?
Yes.
So up to conjugation, they are the same. So let me write it. So if we put the defect at j minus 1, comma j, it's the same as um h j plus 1. I will not bother to write the things that are not important. And j is e to the I, eta m. The strength here is the coefficient by how much we move. And what we have to put here is the corresponding current density at j. And again, we have this picture of a defect here, and we slide it around using the current. Sorry, I misspoke. Yeah, this is the one that shifts it. I copied the wrong one from here. This is the one that shifts it. And the one that implements the shift by 2 pi, whoops, it's here. H of eta is the same as e to the I, e j plus 1, h of eta plus 2 pi, e to the I minus I, e j plus 1. So the details are not important. The important thing is that the fact that it's 2 pi periodic, it's true, not strictly speaking, but only up to conjugation. And we can shift the defect around. Now we see the first subtlety in this model. Imagine we have a bunch of defects. So we have one defect coming here, we say eta m. And another defect coming here with eta w. And I would like to slide them. So as I told you, I can take any defect and just slide them and fuse them. If I fuse them, the etas will add. And now I'm going to slide them. Okay, so I'm going to slide this one to the right. I already learned how to do that. And at a later time, I slide this one to the right.
Sorry, eta will add up means what? It's like two different kinds of eta.
And then I slide it to here. And then I have here eta 1 plus eta 2. That's what I mean by fusing.
I see.
I just do what I did here. Just keep using these conjugations. But this is much more interesting. So imagine, as long as I have only momentum defects, no problem. I can move them around. If this thing is too large by 2 pi, I can conjugate again and bring it back to the fundamental domain. But what happens when we have both? I could slide them in this order, or I could slide them in this order. Could slide them in two different orders. And if we could think of that as different trivializations of the same gauge field, we should get the same answer. Because what we did was to change the places where the transition functions are, but we are going to do that in two different orders. So this is eta m, this is eta w. So we have two defects. We would like to move both of them. So we can move them in this order, or we can move them in that order. Do we get the same answer?
No, because the densities don't.
Because the densities don't commute. And instead, they don't commute, and therefore what we get here is a phase, e to the I, eta m, eta w, over 2 pi. This is an anomaly. We have defects that naively I can move them around, no problem. As I explained that many different ways. I can, as I change the trivialization of background gauge field, I should get the same answer. But here I get the same answer up to 2 pi, up to a phase. Not only that, imagine I started with this guy with eta, with this guy shifted by 2 pi, this thing shifted by 2 pi, then I don't even get the same phase. I don't even get the same phase. They differ by e to the I, the other eta. So even though so this, what I had on these blackboards with all these conjugations by unitary transformations, the fact that things were not true on the nose, but they were true up to conjugation, left the door open to the fact that these conjugations might satisfy funny algebra. That's an anomaly. In this presentation of the anomaly, in terms of defects, is preferred to the one I started with. Because the one I started with assumed that there are currents, the symmetry is U1, and there are currents and conservation laws, etc. And that's a traditional presentation of anomalies, starting with pi to 2 gammas, and then in this Katsuri algebra. But we can take this Hamiltonian and break the momentum and winding symmetries to discrete subgroups. We no longer have currents, we no longer have even charges, the group becomes a finite group. This picture is still correct. So the thing that is always true, whether the group is a continuous group or a finite group or a discrete group, is that we have defects. The defects are labeled by conjugacy classes of the group. But then when we start moving them around, or we try to pick different representatives of the same conjugacy class, things work up to phases. And that's what I emphasized at the beginning of in the first lecture.
But what are current densities for discrete symmetry?
Excellent question. Is there any? No. No. However, what I said here is still correct. So that's the reason it's good to have a solvable model and present it in a way that can be used even when it's not solvable. So I can take this model and break the momentum symmetry to Z7 and the winding symmetry to Z15. And there could still be an anomaly, and the anomaly will be detected in this form. There are no currents, there are charges, not necessarily charge densities. Right? Their charges are finite groups, they're unitary transformations that implement it. Almost everything I said goes through. And the defects, moving the defects around, they don't commute, and we have phases. So this presentation is preferred because I can use it even when I don't have, even when the model is not solvable. And even when the group is a finite group. I'm making no claim that this is the most general anomaly that can exist, but in many cases that I studied, you can turn the anomaly to be just that. If they're defect, they should be labeled by conjugacy classes of the group, and I start moving them around, and the answers, as I move them around, I get mistakes by phases, and also when I pick different representatives in the conjugacy class, I also get a phase.
So let's say gravitational.
I'm not discussing gravitational anomalies. I will, however, discuss anomalies in translation, but for that you'll have to wait maybe by the end of today.
So this is
Till the end of my talk today. If not, it will be the next talk. Yeah.
Is it kind of very, is it kind of Hamilton M space?
I think the answer is yes. I think you can describe it as Berry curvature because you can think of these etas as parameters in the Hamiltonian, and the shifting by 2 pi is reminiscent of the Berry curvature. I'm sticking to this language, which is closer to what we would call with the Toft.
The curvature could be local. I don't think you have to make a whole shift by 2 pi. It could go in the eta space.
Yeah, but you have to do something non-trivial.
Yeah.
You have to do something non-trivial there. I think it's worth analyzing here. And this model is so good because it's very, very explicit, right? We don't need any numerical work or whatever. We just do it.
If I think of it like it's Chandes-Miller terms, like it's a family of Hamiltonians which are labeled by etas at different sites. And so that space has some.
Yeah. But here it's more because I also allow them to move. So I'm using this unitary transformation. And that finally brings me to your other question, Nikita, because I said the word move. So what did Nikita ask? Nikita followed the dogma that when you have a symmetry, you have to use it. So what's the symmetry here? We have ZL of translation. We can also have DL if we include also parity. It's the dihedral group, but let's not discuss it for the moment. So we have ZL of translation. And before we introduce any defect, there is a generator of translation, which we denote as by T. And it is defined as follows. Every local operator, OJ, if I conjugate it by T, I get the operator at the side J plus 1. And this T satisfies the group relation T to the L equal 1. How does this change our story? So if we don't have any defect, that's straightforward. This is just translation. What happens when we have a defect? So with a defect, H, in general, has various etas, does not commute with Y, because we prefer the point, pick the point where the defect is, and I use translation and it moves it to another point. However, I told you how to bring the defect back to where it wanted to be, because we have a unitary transformation that brings us back. So if I compose this T with a unitary transformation that shifts the defect, I could find something that commutes with the Hamiltonian. So it will be a lot of writing, but I think it's worth doing it. Because, as Nikita anticipated, there will be something funny coming out. So we have a Hamiltonian, which has a defect on the link j plus 1, and another defect at the point j prime. So this is at a link, and the links are eta m, and there's also eta w at the site j prime. Right? This is our Hamiltonian. I modified the p squared term at one side, and I modified the delta phi plus n squared at one link. And we would like to see that it is a symmetry. So there is an operator, T eta m, eta w, depends on both, such that T of this H, which I'm not going to write again, equals this H again. This is T of eta m, eta w. Oops. So I'm saving time by writing, and it's unclear. So it's T eta m, eta w, H, j plus 1, j prime, with the etas, T, eta m, eta w, inverse. So this T is composed out of, let me write it, it's the transformation that shifts the momentum defect, j plus 1, and the winding defect, j prime plus 1, times t. So this looks very complicated and lots of indices, but it's very simple. We started with two defects, one here, say momentum, and one here, which is the winding. And we applied t first. When we applied t, they're not at the same place. So this moved here, and this moved here, one side. But then we learned how to bring them back. So we bring them back to where we started. And we came back to where we started. So the original Zn that we had, the original t is no longer there. However, we have instead essentially the same thing. But the fact that these u's don't commute has interesting consequences, because this is a little bit of a computation. But because you can ask t eta m, eta w to the nth power, what is it? So it's a completely straightforward calculation, because I told you what it is in terms of the unitaries and the original t. So I can just write it L times and see what happens. And what do we expect? On general grounds, we expect it to be e to the I qm eta m plus qw eta w. Because that's what twisted boundary conditions is all about. We take something around and we come back up to the group element that we twisted by. We had that in the first lecture. That's what defects are. Now, question number one. Should we put here the qm that was shifted by eta or the original one? Any votes? Should this be, we have already seen that the charges are modified in the presence of another defect. The momentum charge is modified in the presence of the winding defect, and the winding charge is modified in the presence of the momentum charge. So on general grounds, we expect something like this, but which one should I take here? Should I take the original one before I put the defect, or the one after I put the defect? Any votes? Okay, one option is that I'll get the same answer. That's the wrong answer. Another option, take the momentum, but not the winding. Another option, take the winding, but not the momentum. That doesn't sound very democratic, although perhaps today it is appropriate. Right?
By some quadratic phase.
Sorry?
Add an extra phase.
Yeah, everything is, this story is about the phases. The story is about the phases. So option one, I take both the untwisted ones. I'll soon write the answer. Option two, I take both to be the twisted one. I'll soon write the answer. That doesn't give us this equation. And then I can take either twist the momentum but not the winding, or the other way around. But why twist this and not the other? That's the anti-democratic one, which appropriately today turns out to be the correct one.
So which one you do
Doesn't
doesn't matter.
matter. But if you want to preserve T-duality, and you want to preserve momentum and winding to be on equal footing, you have to sacrifice something. So I'll write the answer. So the correct answer, so now I'll write a correct formula. I can write e to the, so option one, I write e to the I, q eta m, qm at 0. That's the untwisted. Plus eta w, qw at 0. And then there's an ugly phase, eta m, eta w over 2 pi. That's option one. Option two, so no, you take the twisted one, eta m, qm, which depends only on eta w, plus eta w, qw, which depends only on eta m. And then I have e to the minus I eta m eta w over 2 pi. So either of these two choices leave a phase behind. I can have one without a phase, for example, e to the I eta m eta m qm eta w, oops, no, eta m of qw plus the I eta w qw of 0. That doesn't have a phase, and by duality I can also move it to here. So I have various options. If I really like the fact that t to the n is the group element, I have no choice but treating momentum and winding in an asymmetric way. If I think, no, I would like to keep t-duality manifest, I have two options, this or that, but then there is a phase. What happened here? We asked ourselves, what's the group of the problem? The symmetry group of the problem was written somewhere here. It's no longer written here. Was U1 times U1 with some semi-direct Z2. But we also shouldn't forget the translation symmetry. So there's also a ZL. We also have a ZL. So the full symmetry group is U1 times U1, let's ignore R, I'll not ignore anything, and Z2. And there's also the ZL of translation. That's the symmetry group. And what do we have in the twisted Hilbert space? Once we have the defects, the momentum symmetries remain, although I might need to have a projective representation of them because of all these fractional charges. The ZL was twisted by these, but I could perhaps pick a different basis where it's not. But in the end of the day, we have this whole group, and this whole group could itself have projective representations. And the projectiveness, or where the phases are, as always, can be moved around. It could be, did I raise the most important equation? Yeah, I raised the most important equation. That's always the case. So we have T of the etas to the A, which I wanted it to be e to the I eta q m n I eta w q w. That's what I wanted to have. But there could be a phase here. And I could redefine the operators. Take this one to flow with eta and this one doesn't, or the other way around. Then this equation will be correct. But then I'll have the phases elsewhere. The invariant statement is that I cannot get rid of all the phases. I can move them around, but I cannot get rid of all of them. And the key point, which is very important here, is that I should really think about this equation, raising t to the nth power, as part of the symmetry group of the problem. So the symmetry group of the problem involves the internal symmetry and this translation group. And this whole group could be in a projective representation. And next time, we'll get a lot of consequences out of this fact. That first, the translation group could be realized in a funny way, and especially the fact that there could be anomalies with various phases. For example, these phases here that lead to interesting results.
But if you want to get the right continuum limit, where you have translation in front, then you can dictate, no?
No. In the continuum limit, this becomes e to the 2 pi I, the momentum, which depends on the twisted m and w, and we have essentially the same formula. Indeed, if you remember your formula for spectral flow, in the spectral flow formula, P goes to P plus dot dot, and then there is an eta m, eta w term. So the quadratic term in the spectral flow leads to a phase here. So that exists already in the continuum, and I deliberately did not discuss it in the continuum because I said if we do it on the lattice, we might have. This is an exact result on the lattice. So, yeah.
I take,
There's another question?
Now questions.
if I take away the translation, there is still an anomaly in the U1 cross U1.
Yes, there is an anomaly in the U1 cross U1, but I could declare that so the defects don't commute. That's a fact. Should we say that the defects carry fractional charges or not? That's up to you. The fact that the defect carries a fractional charge is because you wanted to use the charge after the spectral flow rather than the charge before. When you study a particle on a ring, are the momenta with theta, are the momenta quantized or not? There is a momentum which is quantized, there is another one which is not quantized, and depending what you want to do, one is better than the other. They differ by an additive C number, and therefore there are two ways to describe it. So that doesn't resolve the question. However, if you throw in this equation, it does resolve the question. Why is this important? When we discuss an ordinary quantum mechanical system, forget the fact that it's field theory, we can have various defects, and all there is some projective representations of something. That's all there is in quantum mechanics. This system is a field theory, namely, we have some notion of locality in space. And when we have notion of locality in space, this thing is very important, this equation. And therefore, this equation carries a special role, plays a special role. And once we throw in this equation, so specifically, I would like this T to act away from the defect the same way it acted before I put the defect. So I have a system, this is space. I draw it as a line even though I have a bunch of points. And I have a defect here. And I want this thing, which is the translation generator that commutes with the Hamiltonian, to act around here the same way it did when there was no defect. This is where locality enters. All the defect did was to change things around here, out here. So I impose the fact that T acts here the same way as before. So I'm not allowed to take the phase that existed here and bring it to the left-hand side, because then it will not act the same way as before. So I have T with a well-defined normalization, right? Because I want it to act the same way as before. These have normalization. If I put here the coefficient to be 1, I no longer have the freedom to redefine these Qs. So if I just view it as a group, if I just view the whole thing as a group, I can get rid of some of the phases. But if I also insist on locality, I cannot. So the key point is that I have to impose locality away from the defect. So away from the defect, the operators are the same as they were before. And that's where field theory differs from quantum mechanics. We thought of this system as a system, a random collection of quantum mechanical degrees of freedom. With this symmetry, I could get rid of some of the phases. But I don't because of this notion of locality. So that's why this equation is so important. Because T has a natural normalization, natural phase. That constrains the phase here and eliminates the freedom to redefine some of these. I might not be able to do that, but all I'm saying is that there is less freedom because of this equation than without it.
More questions?
If I want to have something which is localized in space and time, like a model vertex operator on lattice, is it equivalent to a combination of defects moving one way or another? Or
Sometimes it is and sometimes it isn't. But is it going to be tautological or not?
no. Like vertex operator with momentum.
Yeah, this is Zohar's talk. My defects are all topological. So therefore, then it's a random local operator. There are random local operators, and I'm not adding anything to that. Then there are random defects. I'm not adding anything to that. All I'm discussing is the topological defects. And the topological defects have this story with them, with all these phases, and this is how they capture the anomalies.
So we know in supersymmetric theories, supersymmetric gauge theories with high dimensions, where the topological effects of high codimension, they actually solve interesting equations as functions of the parameters, probably like equations. So I imagine that here the interesting equation is like this would be confusing with very curvature.
Yeah, that's an interesting point, and maybe it's better to think about it as Various curvature. I tried to stick as close as possible to the 't Hooft view, or the modern view of 't Hooft anomalies, where you have background gauge field and so forth.
Okay, there are no more questions.